the organizers, for inviting me to give this talk. Before really getting started, a couple of things. First, shameless promotion. This book is now out. Just told me he actually has a physical copy in his hands. I still don't have a physical copy in my hands. For most of the people here who are very mathematical, probably buy the book so you can read about how a condensed matter physicist thinks about some of these things, and hopefully I didn't botch the mathematics too much. If you don't want to pay the whatever 60 pounds to buy the book, you can actually download a lot of it from my website in not quite the final form, but close to the final form, so you get an idea. The second thing is, this is something I'm not going to talk about. This paper I wrote with Yost and now also with Kim Cooney, a graduate student at Maryland. I'm happy to discuss this offline. Yost and I, we got some really horrible referee reports from mathematicians telling us, you guys don't know anything you're talking about. We obviously said some things that were not using definitions incorrectly and so forth. And we want to try to figure out what, because we believe we've done actually something, and we want to figure out how to say it in a way so it makes it clear that we haven't completely messed everything up. So happy to discuss this one offline also. Okay, this work is done with Jovan Jovanovic, Carolyn Villa, and Dan Timmers. And as I was just saying before, judging from the questions of the audience in the last hour, I may have aimed this completely incorrectly. So it's maybe better if we go slowly and don't make it to the end of the talk, and ask whatever questions you find interesting along the way. Also, Dan Timmers is still he worked with me a whole year and a summer ago as an undergrad, and he's fabulous if he applies to you for a PhD position. I recommend you take him. So I'm going to start with a little bit of history, or at least history as I see it, of some of the important things in this field. And the beginning of anions was really in 1977 with this breakthrough paper by the two Jans in Oslo, Jan Magnalinus and Jan Murheim, who pointed out that in 2 + 1 dimensions you can have particles that are neither bosons nor fermions. And from this, you might be tempted to conclude that, well, first, everyone in Oslo is named Jan. I promise that that's actually not the case. Per and Bjorn are also, Jan is the most common name for a male in Oslo, it turns out, but not the only name. But anyway, this work was kind of ignored for the first couple of years of its life, but then it rapidly became rather important. 1982 is the experimental discovery of fractional quantum Hall effect, and within very few short years, it was theoretically understood that low energy excitations of fractional quantum Hall effect really should be anions. And it was a while before there were any experiments that really pointed to this, as experimental evidence that this is really true. One important step was made in the late 90s, where people managed to measure the charge of the excitations in the fractional quantum Hall effect and showed it was fractional. It was done originally with shot noise measurements, but then later on it was done with several other techniques as well, and it's really beyond any doubt at this point. But then trying to show that when you braid particles around each other, you get a phase that is neither +1 nor -1 turned out to be rather difficult. And there were many attempts over the years to do this. Some of these attempts claimed success. Some of them were not convincing, and some were later discovered to be incorrect. And it was finally in 2020 that several papers came out that actually managed to do this right, and now I think we have very strong evidence that these particles really are anions experimentally. There was really no doubt theoretically that they would be, but actually measuring it in experiment was quite hard. And these are several different techniques that all came out at the same time. In particular, point to the work by Nakamura and Manfra and collaborators, which is a fairly direct measurement of the braiding statistics using interferometry. And as we were just saying out in the hallway, there was nothing particularly, why did it take so long? They had to sort of figure out, what were the difficult pieces? Why wasn't it working? Why were the general ideas that people had before not giving the right result? All these things had to be sorted out. And then when they finally did the experiment, it actually didn't seem to be that difficult. So it was, once they know what to do and how to do it, it's not that bad. And so maybe we can be optimistic about other anions that we're going to measure, that there will be a breakthrough, and then all of a sudden we're going to be able to measure them as well. Yeah, okay.
Do you know
No,
if
go
there were any like? At what point was the technology there? Like the materials were good enough?
I think in principle they could have done this experiment around 2000 as far as the mobilities they needed. There weren't any major advances in MBE. I mean, I think they had to realize what it is they had to do, but it wasn't, the materials were good enough by that time, I think. Maybe even a little earlier. Other questions? Yeah.
Actually, Jon Lijnhaas and Jan Meerhuis, so they.
Jon?
With an O, yeah. Jon and Jan.
So no one in Oslo is named Jan. I apologize to both of them. Oh gosh, that's rather bad. Okay. Anyway, so these were all abelian anions, abelian representations of the group. The history of non-abelian anions started around the 1980s as well, and is a little bit more murky. There's some work on non-abelian gauge theories, particularly Sander Bias's work. And I think the first paper to talk about non-abelian representations of the braid group is this one-page paper by Golden, Menikoff, and Sharp, which is actually a comment on another paper. It's a very beautiful little note that explains that yes, you can have particles which display non-abelian representations of the braid group. And then a lot of ideas started coming together in the late 1980s. There's the Witten-Jones polynomial paper. There's this sort of lesser-known paper, including Witten, Chen Wilczek, Witten, and Halpern. That paper was concerned with anion superconductivity. They were thinking about abelian anions, actually. But Witten, of course, having just done the Jones polynomial work, inserted a long discussion of, yes, you could possibly have non-abelian anions in condensed matter as well. Halpern told me somewhat later that he had no idea what Witten was talking about, but I let him put it in. But you know, at the time, don't quote me on that. I probably understood what Witten was talking about by the time it was published, but I can imagine that when he was talking to Witten, he didn't have any idea. Then, and the work by Friedenhagen and collaborators and Froelich and collaborators really working out the structure of what we call modular tensor categories in some form in the early 1990s. Then a rather important work by Moore and Reed showing how fractional quantum Hall effect can display non-abelions in some rather natural way. And then there was a bit of a break, but a rather important breakthrough by Roelof Morph doing numerical work showing with pretty convincing numerics that the state we observe in experiment, the nu equals 5/2 fractional quantum Hall effect, probably is non-abelian things of matter, which we still believe, although we believe very ardently this. There's a lot of theoretical reasons to trust it, but there's no strong evidence of this from experiment. There have been many attempts to measure non-abelian statistics and some non-convincing claims of success along the way, including the entire Majorana effort of Microsoft, which fell on some unfortunate times. And there's continued attempts possibly by the Microsoft group, I'm not exactly sure what they're doing, an experiment, but also Bob Willett still attempting to do experiments on the 5/2 state. But I think the fair assessment is that it's still not there yet, and we don't have any evidence of non-abelian statistics in condensed matter experiment. Anions and quantum computers sort of starts probably before we thought about quantum computers with work by Wen, introducing the notion of topological order, and then this breakthrough paper by Kitaev showing that when you have topological order, you basically have a quantum error correcting code of some sort. I'm going to be a little bit more liberal of what we call a topological quantum error correcting code than Meysam did. He insisted that those are ideal models, but in principle, you could, with great difficulty, use a topologically ordered system, which is not a fixed point model, as a quantum error correcting code. It does store the information as well, just in some complicated way. This brings us to the sort of dichotomy that Meysam discussed very well, that on the one hand, you have Hamiltonian realizations of topologically ordered matter, where you have a ground state of some physical system, and you get to the ground state by cooling down when there's excited states of this physical system. That those excited states include anions running around. If you're on some non-trivial topology, there's a ground state space, and you get into the ground state space by cooling. On the flip side, you have a quantum error correcting codes, where the analogy of the ground state space, the vacuum sector, the TQFT, is the code space, and you get into the code space by doing error correcting. You find your defects and you bring them together in certain ways to annihilate them and get yourself to the vacuum sector. I think it's fair to say that no experiment of any sort has convincing evidence that it's stably in the ground state code space. So whether you're thinking about quantum error correcting codes, we've not achieved, quantum error correcting that lasts forever. Things last for a certain amount of time, and then the wave function wanders off in some random direction that you can't control. In principle, we can do this quantum error correcting, but in practice, we haven't been able to do it yet. In condensed matter, you get to something that looks kind of like the ground state, but we don't know whether there's not one anion running across the system or another anion running across the system. The ground state is probably, or the low energy space, is probably scrambled pretty well over some time scale. So no experiment of any sort is stably in the ground state or the code space. Okay, everyone happy with that? So we're not there yet.
Even at 0 temperature, you mean?
Well, we don't have 0 temperature. Presumably at 0 temperature, it would be stable. I mean, you could have trapped quasi-particles, but you might say that's okay. I'm willing to live with that. But I think that
Flying at temperature is as good as any other quantum computing scheme, I would say, right?
well, and I mean, at finite temperature, we know we're going to have quasi-particles running around at some rate, and the question is, what's that rate compared to our experiment? We don't even know that. We can make an estimate of a gap, but the transport gap and the gap that will scramble the ground state may not be the same. Good. That's it. Yeah.
So airspace, is it a well-defined thing in the sense that anything outside of code space can have air can take them there, right? So it doesn't have to be a subspace. It can be anything to complement.
Yeah, I would just say error space is a complement to the code space.
Okay.
Maybe I'm not using the word space incorrectly, but I would say everything that's not code space is error. I would call error. So history of abelian anyons and quantum computers. There's been lots of work on producing the surface code, or the toric code. And the reason for this is because that's the most efficient, or practically the most favorable code that we know of. For a lot of reasons, it's fairly simple to implement, and it has a very high error threshold. So everyone who's building a quantum computer, not everyone, but a lot of people who are building quantum computers are aiming towards building the surface code. So everything is optimized for making the toric code. Here's one particular one from the Google group. This was an older paper by a Chinese group, Song et al., and even older work by Walraff, demonstrating braiding of elementary particles in toric code. This is a particularly nice one because they do it on a fairly large system, and they take an E particle around an M particle, and they measure the phase. And if you look on this plot, it's the top thing labeled D up there. They take E around M, and they measure a phase which is very close to pi phase, which is what you expect. And it's a very nice demonstration of the topological order and the braiding of the anyons. Actually, in the very same issue of Science in December of 2021, there was another paper that also made toric code topological order using an array of Rydberg atoms. Possibly Nat will talk about Rydberg atoms. No. Okay. But from a lot of the same people who work with that. Anyway, from Misha Lukin's group, they don't measure braiding exactly, but they measure some other things that indicate that they have topological order to some extent. Non-abelian braiding experiments, well, there was nothing before 2023, but in 2023 there were a number of experiments that came out simulating non-abelian anyons and modern NISQ devices. NISQ is near-term intermediate scale quantum. In other words, the current quantum computers that we have right now that really aren't very good. I mean, they're great from the standpoint of what we've been able to do before, and they're terrible from the standpoint of what we hope to be able to do in the future. So, intermediate scale. So there were two experiments which are really very, very similar to each other, one from the Google group and one from the Chinese group. These are terrific machines they have. They're, 70 qubits or 60 qubits or something like that. They can handle circuits of a depth about 100. That's a terrible measure of how deep your circuit can be, but basically just think about being able to do 100 operations on each qubit before the wave function wanders off into some random direction. Of course, it depends what operation you're doing and so forth, but 100 is roughly the kind of number. The thing that's difficult about these machines is these machines' measurement is really expensive in the sense that it takes as much time and sort of decoherence resource to do one measurement as it takes to do 30 operations, more or less, 30 or 40 operations. So when you do an experiment with a superconducting quantum computer, at least with this particular design, you have to minimize the number of measurements that you do. So you set everything up, you do whatever you're going to do, and then you measure once at the end to get the output.
Are you saying spam is bad? Spam errors are bad?
Spam errors?
The preparation and measurement of states, is it the errors that are bad, or is it that the time is bad?
It's the time scale and the error. There's also error induced, but it's basically the time scale, I believe. I think that's right, although someone can correct me if I'm wrong on that. Anyway, I was told never measure on these machines if you can avoid it. So these machines, this particular set of experiments, these are not non-abelian anyons in the conventional sense. They're very carefully worded the way they say this in the title. These are carefully, they call it either graph vertices or defects or projective anyons. Is exactly what Mason was talking about.
Both of them were careful, right? Projective, no,
Projective, yeah, they were careful. Although I will note that the first version on the archive was not careful, so I suspect.
Some learning curve there.
To be more careful. This scheme is basically the scheme that in Kitaev's original paper. He points out that if you have the toric code and there's a lattice dislocation where the lattice is connected together incorrectly, that dislocation stores a Majorana zero mode, which basically looks like an anion, and then it was expanded by Bombin and then by Mason and friends later to say that, well, you can braid these things around each other just as well. The topological order that's there is really the order of the toric code. I mean, if you think about what is the vacuum state of your system, it's the vacuum state of the toric code with no defects there. What are the low energy excitations of the vacuum state? They're the low energy excitations of the toric code. You have to by hand put in a defect by reconnecting the graph, the lattice, and those things are the things that you then braid around each other. It has a lot of the properties of non-abelian anyons, but not all of them are slightly different properties. And the reason this was an easy experiment for them to do is because they had optimized their machine for doing the toric code, because everyone's interested in doing the toric code for quantum error correcting purposes, so it had been really optimized for building exactly this. So the years of it, yeah.
Does that mean like they had the physical qubits are arranged in a 2D lattice in their machines?
Yes, yeah. It looks like this, exactly like that, so it's really in a 2D lattice, and they basically just do a long range connection between long range connection between two of them. Okay, so the other experiment that came out at roughly the same time is topological order with trapped ions, and I assume Nat's going to talk about this. I have the name underlined. I'll only say one or two words about it. What ions have that superconducting qubits don't have is they have measurement, that you can do fast measurement on ion computers. The ion computers have some other liabilities. They can't go to the same depth, but they didn't need a huge amount of depth to do what they were going to do in this experiment. So the way this is prepared assume Nat's going to talk about it, is a measure and feed forward protocol, which involves, you set something up, and then you make a measurement, and you find some anions, and you try to bring them together to get rid of them, and that brings you to the code space. The order that they made is Morito equivalent to D double of D4 topological order. It's 22 anion species. They confirmed the 22 degenerate ground states on a simulated 3x3 torus. So in this particular experiment, the actual physical ions are in a line, well, actually in a loop, a big racetrack. And they simulate, you never ask if you're simulating, some lattice model on your computer, you never ask, well, where are those memories in the computer? You just assign it, this is site 1, this is site 2, this is site 3, and at sort of the software level, you imagine connecting them up, and that's what they did here. They put the ions on there in their one dimension, and they say this is going to be site 1, this is site 2, to try to make a torus. So it's a simulated torus, but they confirmed the 22 degenerate ground states. There is there's a potential complaint about that, which is that one of the things that we really like about a topological order is that it's immune from any local perturbations. And here you've totally destroyed locality by moving the ions all over the place.
Then again, topological invariance allows you to move everything around. So.
But now you have things connected to each other which are very far apart. And so you can have a local noise in this system which is non-local.
Noise gets distorted.
Gets distorted.
But in terms of a state,
but I would say
move
that
things around.
There's a better reason to ignore it, which is that none of this is error protected anyway. The system is not error protected. We're not even trying to do error protection at this point. There's no point in trying to say, well, the type of noise is local, so.
But in any topologically ordered theory, the concept of position is washed out anyways, right?
But locality is important to preserve.
Of errors. No, it's a different issue.
So yes.
Topological order doesn't care about position. I think that's.
But you do care that the order, but that the errors are going to have local noise.
Error, yes.
I think
Additional characteristic, yes.
Okay. They also managed to show one example of non-abelian braiding of anions, which I think that will. I'm telling you what you're going to say, but I suspect you are going to say this. But there's a lot more to do, and that's what I'm hoping to talk about. So this is a paper I'm going to talk about. It's a little less exciting than what I just talked about because there hasn't been an experiment yet. What we did in this paper was we designed an experiment it was designed for a group whose name rhymes with Google. I won't tell you which group that is, but you can guess. Well, that was a joke. We had this long discussion with Google over the course of many months about doing this experiment, and in the end we couldn't convince them to actually do it. And I think part of the reason, there are several reasons, some of which I think are actually valid, that they felt they had already done a braiding experiment, and they have a very high bar for what experiments they want to do, because if it's not on the front page of the New York Times, it's not up to their level. They're very, they sort of keep a very high level of limited experiments they can do with their machine, and they really want to choose the best ones. So they felt this one didn't cut it for certain reasons, and they felt they had already done something of the sort, so they didn't end up doing it. But we now have another experimental group who is working on it right now with a machine that's fairly comparable to Google, but I've been told not to say anything yet about the experiment because it may actually not work out as well as we thought. But anyway, this is where we're going. So just to remind you, the two routes to non-abelian behavior, which I think I emphasized just a moment ago, there's the defect route, the G crossed blah blah blah, which is what was done by the Google group and the Chinese group in the superconducting computers. And there's the real topological order, which is done by the Quantinuum group, and which we'll hear about. I think it's fair to say that they're different beasts to some extent, although they share a lot of properties. This is the one we're going to try to do on a a superconducting computer. So the kind of experiment we want to do is we want to, and the challenge we have, or at least one of the challenges that we have, is we can't do feed-forward experiments because those computers' measurement is really expensive. So the kind of experiment we want to do is we want to do fusion experiments where you bring two anions together and see the multiple fusion channels. We want to do non-abelian braiding experiments where you show that the order of braiding matters. And we want to actually measure the S&T matrices, which, as you know, are important properties of topological order. And you might say, well, why do we want to do this? And in some sense, this is an exactly solvable model. It's not going to be a surprise. If you've done it right, you get the right answer out. Oops. Well, okay, I think I put that little blurb somewhere else. But I'll tell you now. The reason we want to do this is not because it's going to be a surprise what comes out. We believe we know what the answer to all of these is going to be because it's exactly solvable. The reason we want to do it is because we want to see how much we can do on these computers so that then at some point we will start simulating models where we don't know the answer. We're sort of honing our techniques for being able to do things in the future. Or maybe we're testing our quantum computers at what their capabilities are. So here are the kinds of experiments. Fusing anions together, so the big red blobs are my anions, and I move them together with gratuitous animation, and they form some other particle, and you measure the particle type, and you show that there's multiple fusion outcomes. We want to do non-abelian braiding experiments, so the kind of thing you do is you pull pairs of anions out of the vacuum, then you maybe braid the two in the middle around each other, and then the two on the left hand around each other, and then you bring them back together. These should always annihilate back to the vacuum. On the other hand, if you do it in the opposite order, braid the two on the left around each other first, and then two in the middle around each other next, and you bring the two in the middle back together, and the two in the right back together, then they don't necessarily fuse back to the vacuum, and we'd like to see that, so the order of braiding matters. We'd like to measure the S matrix. I suspect everyone knows what that involves. Take anions of different species, braid them around each other, bring them back together. It may or may not fuse back to the vacuum, but we're going to select on the cases that go back to the vacuum and measure the phase and amplitude of that process. And also T-matrix experiments, we want to measure the accumulated phase of a single exchange if we can. So those are the kind of things we want to do. S&T matrices in particular are something of interest that hasn't been measured for any anion theories in any experiment, and we'd like to be able to do that. That was one of the selling points that we tried to show that you can do. So S&T matrices, as you know, don't quite fully define an anion theory, but they almost fully define an anion theory. Some people in this room have worked on that quite a bit. But being able to measure S&T matrices would be a very nice thing. Okay, there's the little verb I have. We hope to really, the point of doing all this is we want to learn tricks that are going to be useful for doing more experiments going forward. So we want to see what we can do, and then once we have our toolbox of tricks that we can use, then hopefully we'll be able to do things where we don't know what the answer is, like perturbing our topological quantum field theory and playing with that. Okay. Again, I just put this here to remind people that we're over here. We're going to be in this quantum error correcting realization of topological code. There's no Hamiltonian. We're not trying to cool down the energy. We're just trying to prepare a wave function and bring it into the code space and do experiments of the code space. No experiment is stably in the code space. It's not error corrected in any sense. So that means you have to prepare it in the space that in the code space that you want, in the TQFT space. Do your braiding experiment as quickly as you can, measure it, and hope that you've done it fast enough before it's just wandered off into to randomness. Okay, everyone still happy?
Well, there's no Hamiltonian, but in some conceptual sense, the code space is lower energy.
Well, the code space isn't lower energy. I mean, if you can write down an imaginary Hamilton, not imaginary like in complex,
Made up.
but made up Hamiltonian, for which this would be the ground state, and think of this as being exactly this. So you can make up an effective Hamiltonian or something like that the code space would be the ground state of.
Are you going to use a stabilizer code at all? Because that will have a Hamiltonian that maybe you're not working with the
We're
rest.
not using it. Yes, yeah, we're going to use it. Well,
So you'll use
it's-
stabilizer measurements.
strictly speaking, it's not I was corrected on this. Strictly speaking, this is not a stabilizer. It's a commuting projective Hamiltonian. Doesn't mean stabilizer. Yeah, it's not. Yeah, I shouldn't call it stabilizer. But it's commuting. We're going to use commuting projector Hamiltonian, but we're not using the Hamiltonian. We're just thinking of it as measurements. Yeah, yeah.
So, quick questions. So would it be enough to just show that sigma 1, 2 is not sigma 2, 3?
That sigma 1 is not equal to sigma 2, 3.
Yeah, right? Because if it's abelian, then the dimension is 1, and they differ by a factor of d, right?
I think. So someone might say, if you want to show non-abelian, you have to show two things don't commute, and then you're trying to do this in a direct way.
Okay.
Yeah. Okay. Good. Okay. So what model do we want? So this goes. I suspect everyone in the room already knows this model, but maybe some people don't. So this is in Kitaev's original paper where he wrote down the toric code. He also introduced the so-called quantum double model, which is the non-abelian generalization of the toric code. It's quantum double of a finite group. It's also in a different language. It's a discrete lattice gauge theory, Hamiltonian formulation of a discrete lattice gauge theory in dimensions. And importantly, if you choose the right group, this model is computationally universal if you can do measurements. Now, the group we're going to choose is in fact not computationally universal, and I'll come back at the end to what happens if you choose a different group. So with a little bit more detail, or to remind you, you start with some graph without endpoints. So these are supposed to go off to meet up with other lines. It's supposed to be some graph without endpoints. And putting arrows on each edge. This is a regular lattice I've drawn, but it doesn't have to be regular. You label each edge with a group element, and if you reverse the arrow, you invert the group element. Then the Hamiltonian, the fixed point Hamiltonian, is a sum of two terms, vertex terms and plaquette terms. I've conveniently not chosen the same convention as MESOM, and put the flatness term on the vertex and the gauge invariance term on the plaquette. This is actually opposite. I'm working on the dual lattice compared to Kitaev's original convention. People who like to work with string nets tend to use this convention. People who like to work with gauge theories work with the other convention. I apologize, we had to choose one. We're going to make half the people angry either way. So the flatness term, so these A and B operators they're all commuting, they're all projectors, the eigenvalues are +1 and 0. The flatness term assures that G1 times G2 equals G4 times G3 at every vertex, or going all the way around the vertex G1, G2, G3 inverse G4 inverse the identity. The gauge invariance term, you multiply by G at all the legs going around the plaquette, and then you sum over G and divide by the order of the group. These are all both projectors. Just again, this comment that I've written down a Hamiltonian, and the code space is the ground state space of the Hamiltonian, but we're really thinking about these as being syndrome measurements. Okay. The anion spectrum of the Kitaev quantum double model includes several types of particles. The charges, these are the ones that violate the gauge invariance. That's this. They include fluxes that violate the flatness condition. Here, this is a little inconvenient now that the fluxes happen to be at the vertices, but okay, this is the problem with choosing a different convention. The charges are labeled by the group representations, and the fluxes are labeled by the conjugacy classes. And then you have dions that violate both, and probably you guys know as well as I do that you need the representations of the centralizer of a element class to count them all. Just for example, we're going to need non-abelian anions, so we choose the smallest few non-abelian groups. S3 has 8 anion species, 6-element group. D4, 8. D4 is the symmetries of a square. It's an 8-element group. There's 22 anion species, and Q8, the quaternions, also has 22 anion species. And the operators we're going to think about are ribbon operators that create and move anions, and we want to do these braiding using matrix experiments. Everyone still happy? Okay. Why do we want to do it? Well, despite the difficulties, it can pretty much be done now, you think. Okay, we're going to make the first non-abelian anions and superconducting qubits. I mean, why do we want to do it? To some extent, you do it for bragging rights, right? You want to be the first person to do it. But the real reason we want to do it is we want to be the first person to measure the S matrix of the non-abelian anion theory. First people to measure the T matrix of the non-abelian anion theory, if we can do it. But really, the real reason we want to do it is because we're trying to learn tricks that will help us go forward and do other things. Yeah.
Is the goal to get the entire S matrix or just part of it?
I would like to get at the whole thing, and I'll show you that there are little pieces that are pretty hard to get. Yeah.
Is there any sense that you can't simulate this on a classical computer? Is there like a quantum supremacy element going on here?
Well, I will tell you that everything here you can do with a pencil and paper. So it's not surprising. Nothing is going to be a surprise. So now, if you took this model and you perturbed it, then you can't do it. Ask what happens. So you might say, well, let me choose the perturbation to be the noise in the quantum computer. Now it's very hard to simulate. Okay? And in fact, this is exactly what we did. That we try to do these experiments, and we then actually, because we're trying to tell the people to do the experiment, and then we simulate it on a classical computer, and it actually starts to get really hard because you need a really big computer to simulate it once you put noise in.
So the fact that it's exactly solvable means that it's solvable. Like you can just do it with your pencil and paper.
As long as you don't have noise, and as long as you don't have any perturbations to the model.
But naturally, it does have noise and perturbations.
Yeah, exactly. Yeah. Okay. It's not it's not easy even though it's exactly solvable, or we're trying to do something where we know the answer. So why is it not easy? The smallest non-abelian group has 6 elements. That means you need 6 qubits just to store the quantum number of a single edge. Okay? Sorry, 3 qubits. 3 qubits to store the quantum number of a single edge. Whether you have a 6-element group or an 8-element group, you're going to need 3 qubits. So that means you're going to start using up a lot of qubits rather quickly. Anytime you move anything, you're going to need gates to make these ribbon operators. And these gate count is going to start getting to be a problem. Each time you put in a gate, there's a chance for errors. It's going to take time. There's a chance for errors. The big thing is that the model is fundamentally based on group multiplication. Why is that? Okay, go back to here. Look at the vertex operators. Here, there's a multiplication of 2 elements of the group. Here, this operator, there's multiplication of 2 elements of the group. So you have to be able to multiply elements of the group. And so you're going to need, I need 3 qubits to store one group element, 3 qubits to store another group element. You need some circuit to give as an output the product of the group product of G1 times G2. Now, this is the circuit that does the trick for D4, the group D4, which we're going to use. And it looks like it's not that bad a circuit, but it's actually terrible because what's hidden in there are Toffoli gates. A Toffoli gate is a controlled not. This, it flips this bit if these 2 bits are on. And actually, with the hardware they have, Toffoli is not a native gate. You have to decompose a Toffoli into between 6 and 12 controlled knots, and 6 to 12 depending on what other native gates you have. So this is actually a really, really complicated circuit. And if you have to start doing that a lot of times, you're dead. Okay? So that's where the problem lies. So this makes us very, very unhappy. Death becomes a problem very quickly if you're trying to do that. So how do we achieve this? So I'd like to say it's one, like you see on the internet, it's this one simple trick. It's not this one simple trick. There's actually several tricks that we used. And well, the first is if you choose the right group, things are a little easier. In D4, actually has a lot of structure to it that makes your life a little easier than other groups you might choose. Actually, the quaternion group isn't that bad either, but D4 is nice. One thing that's nice about the group is that it has 8 elements, and 8 fits nicely into 3 qubits. You can, the generators of the group, it's the symmetries of a square, so there's the mirror operation and the rotation operation, and any element of the group, way up there, can be written as m to the a, r to the b, r to the 2c, where a, b, and c are 0 and 1. So you can write your group element as just 3 qubits ABC. So that's a nice representation. That works nicely, and some of the circuits aren't that awful. The other thing we're going to do is preparing the ground state is really terrible if you don't have measure and feed forward protocols. And the way we're going to get around this is we're going to use a quasi one-dimensional lattice, sort of like a ladder. The ground state's preparation gets much simpler, but it's still enough to do braiding. It's still enough to do the experiments we want to do. So that helps a lot. There's what we call clever circuit engineering is also very useful. And what I mean by this is the following. If you try to, you have some anyons running around. If you try to write a circuit that takes any anion from this point and moves it to this point, that's a horrible circuit to write. It's incredibly long, it's incredibly complicated. But if you know that the anion you're going to pick up is of a particular type, then you can tailor your circuit to say, okay, I'm going to pick up an anion of a particular type here and move it to there. And that's actually a much simpler circuit. So if you tailor your circuit for what you think is going on in your lattice already, then it gets a lot easier. And that's one of the tricks we're going to use. And a third trick is it's a similar idea that if you want, you need to make a measurement at some point to say what kind of anion do I have here. And if you write a circuit that tells you, that measures some region and outputs, this is the type of anion you have sitting there. That's a terrible thing to write down. It's really complicated. But it's actually easy to write a circuit that tells you some property of the anion that's sitting there. So it's kind of like the game of 20 questions. If you've never played the game of 20 questions, someone says, oh, I'm thinking of an object, and the first thing you say is it an animal? And you say, yes. And then you say, is it gray? And you say, yes. Does it have a trunk? No. Is it big? Yes. Okay, it's a hippopotamus. Okay. So the idea is similar here, that you can ask a bunch of different questions about different properties of this anion, and run the experiment several different times, and each time at the end you measure a different property, and then sort of narrow it down to figuring out exactly what the anion was that was sitting there. Okay, and that makes things much easier than trying to write a sort of one-size-fits-all, just tell me the answer in one shot circuit. So the fifth point here is that we can probably do even better than we've done here in our experiments, numerical experiments, because the real experimental groups have lots of tricks that they put in to make things better, like error mitigation, dynamical decoupling. They can change their native gates that they use. So what we did is we used, Google has a circuit simulation software, and with a certain error simulation built into it. And it's actually a pretty decent error simulation for their Sycamore chip. And we just used that, without any modifications. When they actually do experiments like the toric code braiding experiment, they put in dynamical decoupling and error mitigation in order to get the results really, perfect. Whereas if you just did it straight ahead, the results come out kind of trashy. Okay, so we're going to need circuits for ground state preparation, for moving anions around and measuring topological quantum numbers. Let's start with ground state preparation. Again, multiplication is hard because ground state preparation is hard. So what we're going to do is we're going to build a quasi one-dimensional lattice that looks like this. So this is one plaquette here. This is 3 qubits labeling the group element on that edge. This is 3 qubits labeling the group element on that edge. And then this is 3 more on this edge, 3 more on this edge. So you think of this as a set of plaquettes, and then one plaquette fills the outside of the sphere, outside of the whole system. Okay, so that's the geometry that we're going to use. And this is actually really simple to prepare, because the ground state of this is just a cat state, way up in that corner there, of the sum of group element here, same group element here, summed over all possible group elements. It's a really simple ground state. And it's a very simple circuit that does that. You know, you need 3 qubits to store, actually, here it is, 3 qubits, A, B, and C, M to the A, R to the B, R to the 2C, to store a group element. So we have 3 qubits here, 3 qubits here, start them all in the 0 state, Hadamard the top 3, so we get a uniform, you know, an equal weight superposition of all the group elements, all 8 elements for the top 3, then control knot to the bottom, and you just get the cat state of the top with the bottom. Okay, so that's a depth 2 circuit because all those control knots can be done at the same time. Okay. So that's really easy. We did play with doing slightly more complicated, sort of more 2D-ish things that aren't completely in this ladder geometry, like this one here. It's a little bit harder because that does require a real multiplication. You know, to some extent you can do it. You know, it wastes a lot of resources because each time you do a group multiplication, that's wasting some resources. But we did try to do some on this geometry as well.
Steve, I'm a little confused. What do you mean by this fuzzy lumpy lattice? I thought we wanted to prepare states on a torus, right?
Yeah.
So
So
is this somehow doing something on a torus or not?
No, this is, you should think of this as living on a sphere.
A sphere.
This is living on a sphere, but for anyons and braiding anyons, you know, sphere is good enough.
I see.
Make the anyons.
There's no ground state without anyons, but you're gonna.
Well, the unique ground state.
Yeah.
Unique ground state. Yeah. Yeah. Exactly. Yeah. Okay. Creating and moving anyons. So you guys probably know this also, but the operator that moves anyons around is known as a ribbon operator. So the big blue dots are the locations of the anyons, and then there's a so the arrows are, you know, some lattice that they live on, or graph that they live on, irregular graph that they happen to live on, and to get, you know, to pull a ribbon operator from this blue dot to this blue dot, you have to operate on the red direct line going along the lattice, along the red thing here, and then the dual lattice, a line along the dual lattice, the blue thing here that crosses over the green bonds as well. And one thing that's kind of crucial in this model is that the anyons themselves have live in a higher dimensional Hilbert space. So there's, once I've made the anyons of a particular topological type, there's still an internal degeneracy. And it's, this was pointed out by, Serac talked about simulating this model way back in like 2005 or something. And he pointed out that a very convenient way to handle that internal degeneracy is to entangle it with some ancilla that will encode the internal degeneracy of these anyons, which doesn't have, it's not the topological degree of freedom. It's in addition to the topological degree of freedom, and that's going to be stored in an ancilla. Yes.
Can you just go back to the previous slide with the preparation?
Yeah.
So I didn't quite understand. So this is your whole system? Is just this?
So it's one-dimensional lattice, just a ladder like this.
And then
and it's actually, let me put words in your mouth. You're going to say it's not entangled.
yeah.
Yeah. Yeah. It's not, that's right. It's not entangled, and that's why it's easy to prepare. But it's good enough for doing braiding. That this is enough. Because once you drag ribbons, then it does become entangled, and it's good enough.
What is the meaning of the arrows?
That's just the direction of all lines in the model are directed. I could have left those off. But all lines are directed, and if you direct them this way, then the ground state looks like this.
So this planar graph, should I think of it as literally like a triangulation of a sphere or a cellulation of a sphere?
Yes.
Like
Yeah. It's a
the plane of the.
the plane is the rest of the sphere, and then these are some bubbles on the sphere. You can think of it that way. Yeah.
Your formula only show 2 qubits in your ground state? Or
Yeah, because each of the bubbles are unentangled with each other, so you do the same thing for each bubble.
Okay.
Wait, so one is entangled with
Only
two.
2. Yeah.
3 is only entangled with 4.
Correct. Yeah. But then when you pull the ribbons, then everything becomes entangled.
Is this more like a connect sum of spheres? Like multiple spheres, like you have the ground state space on a sphere, but you have several copies of it, one for each of these bubbles.
No, are you saying that I could think of it as, because there is one plaquette that goes around the whole outside. And I think that really should be thought of as a single plaquette.
But have you really imposed the stabilizer term for that plaquette?
Well, if we were doing error correction, we would want to do that. Yeah, but we don't.
Maybe a side comment. In order to show non-abelianity, you can work only with the ribbon operators. You don't need to work with the ground state necessarily. So you can show that the ribbon operators do not commute and they produce actually the braiding property you have without actually acting it on a state.
I think the ribbon operators, in general, the ribbon operators don't have to have the right commutations unless they're acting on the ground state.
Yes, but you could obtain the statistics from them. It's not necessary. Maybe it comes out, so it's not necessary to act it on a state. It happens for many group systems, many topological systems.
So in certain cases, like the toric code, then the ribbon operators will have the commutations themselves. It doesn't matter what you act them on.
Exactly.
But I think in general, you have to be. I think that's right. In general, you have to be acting on the ground state space. So.
I'm still confused by this diagram. So how should I think about this? You have these different unentangled pairs of blocks.
Yeah, that's right.
And then why should I think of this as being related to the ground state of the D4 lattice model?
So so let me take a sphere. I can write the Kitaev quantum double with like one edge if I wanted to, and two plaquettes,
Yeah.
one on the top, one on the bottom. Okay, so I'm doing the same thing, but so let me do just one bubble.
Okay.
Then you have a plaquette on the inside, a plaquette on the outside.
Yes.
That's the correct representation of the Kitaev quantum double model with a sphere and one edge.
Right.
So this is a sphere with several plaquettes on it. So it's one dimensional, so it's quasi one dimensional, so it has fairly simple entanglement. But that's what you would get for these plaquettes, these edges, these vertices.
You haven't imposed a stabilizer on this external, on the plaquette that's external to all these bubbles. You haven't imposed that stabilizer on the state. So morally, there's like two defects. There's charge, right? There's a charge on that.
So if you set it up this way, you get zero charge on the outside. If you set it up in this way, the outside actually ends up having zero charge.
I see. You get that
Yeah,
stabilizer.
you get that one for free. Yeah, because there's always, when you set up on the sphere, there's always you always have a net total charge of zero no matter what you do on a sphere. So the outside always ends up having zero if the insides have zero. Yeah. If you were trying to do error correction, then you're right. You have to. There's one plaquette that's really hard to error correct because it's the outside and has a lot of edges.
So are you measuring? Do a measurement on each of the bubble?
Well, we're actually not, since we're not doing error correction, we're not doing any measurement, but that's what you would do for error correction. You would do a measurement on all the bubbles and all the vertices.
Okay. Yeah, but you're not doing it.
But I'm not doing that, yeah. I mean, you can test that if you pull the ribbon operators down this graph, they all have the right commutations and so forth, and everything comes out the way you expect. Okay, so let me give a description of how these ribbon operators work. So let's take, for example, a flux anion that's labeled by a conjugacy class C. So what you do is you start with your ancillas, and you start by preparing your ancillas in a superposition of all of the elements of the conjugacy class. And then you pull the ancilla from here to, from one point to the other, and each time you go over one of the green edges, you have to conjugate the ancilla by h, the value of the group on the green line that you crossed over. And then each g that you go along, you have to multiply g by the ancilla. Okay, that's how quantum double ribbon operators work. So the ancilla gets acted on by the green guys, and the red guys get acted on by the ancilla. Now, the reason why this is bad is because all of these things are multiplications or conjugations, and multiplying and conjugating are terrible. It takes 45 operations to do a single group multiply, so we don't want to do that. So what we do instead is we do a tailored circuit, as I mentioned, and if I tell you in advance the particle that I'm going to be considering, the flux I'm going to be considering is from this particular conjugacy class, the conjugacy class that includes r and r cubed. Then I'm going to be multiplying by an element of the conjugacy class, but I know that that element is either r or r cubed. And I'm going to be conjugating by a group element, but the thing I'm conjugating is either r or r cubed. And then if you have that information in advance, that the flux is going to be this flux, then I can write very short circuits that pull the ribbon operator. Okay? So by knowing in advance what the particle type is, then you can write a very short circuit. That makes us happy. Okay, measurement. You have to be able to measure the flux. As long as you're happy with destructive measurement, measuring the flux at a vertex is actually really easy, because that's just measuring, so the flux is the product of G times H times K inverse times L inverse, just the total flux going into that vertex, the total group element going into that vertex. If you're willing to just measure all the qubits at the end, then you just measure what's G, what's H, what's K, what's L, and multiply them together, post-process them later at the end of the day, and it'll tell you what the flux is. So you just measure all the qubits, and it will tell you what's the flux at every vertex. Okay. Happy?
You chuck it if it wasn't one. You throw
Well,
it
no.
in the experiment if it wasn't one.
In the ground state is 1, but if I've made an anion, it doesn't have to be 1. Yeah. So if I want to confirm that I've made the anion I think I have, I measure it, but then I've destroyed the experiment because I measured everything. So you do it once. The hard one is measuring the charge. So to measure a charge is a complicated operation. The general way you would do it is you prepare an ancilla in the superposition of all elements G of the group. Then you have to multiply all of the edges around a plaquette by G, controlled multiply on all the edges, then read out the ancilla in the representation basis. And the reason this is hard is because you have to do multiplication. You have to multiply the G by all the edges, and that's a complicated circuit to do. So you don't want to do that. So what you do instead is you play 20 questions, you choose a subgroup of G. And what I'm going to do is I'm going to prepare my ancilla in a superposition of only elements of the subgroup. And then I just need to multiply only by elements of the subgroup. And if I know in advance that I'm multiplying only by elements of a particular subgroup, then it's really easy to make a short circuit that will do this. When I read out in the representations of that subgroup, and it enables me to distinguish between some of the charges, but not all of the charges, but then I can repeat the experiment with a different subgroup, okay? So you run the experiment multiple times, and you choose multiple subgroups to do different reduced charge measurements. So for example, this is a particular, oops, oh dear. All right, something didn't reproduce in this slide. I thought this was perfect. My PowerPoint slides didn't show up here. Anyway, this is a 4-element subgroup that I've chosen, and I can code the ancilla with 2 bits, one MR and the other is R squared. So it's a subgroup that's generated by MR and R squared, and this is a bubble in having 2 edges to the plaquette, and this is the circuit which measures in the representations of this subgroup. And it's depth 4, not 4 factorial. That's 4 excitement rather than 4 factorial. So it's a very short circuit that enables you to measure in that subgroup, and then you choose a different subgroup and you do the experiment again. Okay. All right, so that makes us happy.
Do you do something similar for the dions?
Do it?
The dions. Do you also have to measure out the dions?
So it's not bad, because the dion is going to be some combination of flux and charge. So you measure the flux and you measure the charge, and then you're good. So you can figure out what's a dion as well. Okay, so let's do it. So I'm going to show you a bunch of circuit layouts. So this is the Sycamore. This is our model of the Sycamore chip. And the kind of layout we do is, so each one of these blobs these circles is a qubit, and so the bubbles are these. This is a bubble, that's a bubble, that's a bubble. So this is a 3-bubble circuit. Then you need a bunch of ancillas and a bunch of measurement qubits, And we changed the layout, they give you a ton of information about the particular chip. Certain qubits actually happen to be bad, that they're less good than others, so you try to avoid those. And, so we did a lot of that just to see how good we could do. The simulation we tried to do the simulation on 3 bubbles, and it turned out that was too big to do, because once you throw in noise and all the ancillas that you need, 2 bubbles is about as much as you can simulate. I mean, maybe if we had like a supercomputer, we'd do better, but we didn't, and so that's as far as we went.
Did you do one loop?
Well, with 1 loop, you can't do too much.
Right.
Yeah.
You can't exactly have a long.
But you can do things with 2 loops. So for example, okay, so this is a little bit of a complicated diagram, but I'll try to walk you through it. So this is the particular two bubble layout that we used. So each anion is affiliated with both a vertex and a plaquette. So the plaquette is marked with X and the vertex is marked with blue. This diagram is particularly confusing because the blue X and the red X are actually supposed to be the same point. They're just drawn in different places. So there's a blue ribbon operator that takes the, I can use this with the pointer here. So there's a blue ribbon operator that starts, goes from this point here, which has a vertex and a plaquette, and then goes to over here where there's a vertex and a plaquette, and then there's a red ribbon operator that goes from this point here, which is a vertex and a plaquette, and drags to here, and it fuses those together. And we did another, this is our other setup that we looked at, and it's similar. Okay, here's the starting point, and here's the ending point, and here's the starting point, and here's the ending point, and we fuse them together. Okay, so how, well, okay, here's another gratuitous animation. So, and what we're trying to do kind of looks like this. You make your anions and you just drag them together and you just measure what comes out. And measure it. Okay, so how well does this work? Oh, and which anions did we choose to look at? We did a couple, but just for the sake of presentation, we chose this one, which is 2 flux anions that happen to go by the name of Psi-M. They fuse together to 4 channels. O is the identity. Sigma is the things with twiddles are dions. I think sigma is also a dion. So they get a bunch of things out. Does it work? Yeah, actually it works pretty well. The circuit depth for this is only about 37 long. This is a simulation result with realistic noise. And we did in this case actually the reduced flux measurement is sufficient to identify the 4 particles that come out, 1, 2, 3, 4. And if you do a different reduced flux measurement, this particular reduced flux measurement doesn't actually distinguish some of them from each other, but you can do that one as well. So that seems to work pretty well, and there's, you can see that there's some amount of error, but not an enormous amount of error. Braiding experiments, so the braiding experiment, it kind of looks like this, it's this thing again, exchange the 2 middle, then exchange the 2 on the left, and then bring them back together in the middle and measure the outcome. Versus doing it in the opposite order, exchange the left first, exchange the middle, then bring the middle together like this, and measure the outcome. And okay, those are the 2 processes, and the simulation says it works really well. You can, you get the 4 outcomes in the second case, and only the vacuum in the first case. The circuit depth here is about 60, so it's getting a little bit harder. The hard part is actually the S and T matrix measurements. The phase, the hardest thing is the S matrix measurement, actually. So we're trying to do something like this. If you were only trying to measure the amplitude of S, it's actually easier than the braiding experiment we did. And actually, we probably should have put some examples of it in the paper, but we didn't because it was easier. Maybe in a revised version, we'll put them back in. All you have to do is you do this procedure and you measure what is the amplitude for these fusing back to the vacuum, and that gives you the S matrix amplitude. The hard part is getting the phase. And the reason for this is to get phase, you have to do an interference experiment. And the way you do this is you have an ancilla hanging out down here, and you condition the motion of this guy based on the state of the ancilla. So if the instilla is in the 1 state, you drag the red particle around, and if the instilla is in the 0 state, you drag the vacuum around, you do nothing, okay? And you have to compare those to each other. So the ancilla you start the ancilla in 0 plus 1, and the ancilla comes out in 0 plus S matrix times 1. And then you just do a tomography measurement on the ancilla to get its phase. And this is the hardest thing to do. It's similar trick that you use for the T matrix measurement, but it's actually easier because there's only 1 pair of particles instead of 2 pairs of particles. Again, you take an ancilla, you start in the 0 plus 1 state. You do a controlled twist on the particle. If the ancilla is in the 1 state, you twist the particle. If it's in the 0 state, you don't. And then you bring them back together, and you have to measure the state of the qubit. So the T matrix, because there's only 1 pair of particles in the T matrix measurement, it turns out even for the hardest case, has depth about 90, you get results that are quite close to what you expect. The T matrix for the phi twiddle R particle is a particular dion, which is the hardest one to do. It's supposed to come out -I. Has amplitude very close to 1 and phase very close to 3/2 pi, exactly like you expect. So T matrix is not hard. The S matrix is the hard part. The phase of the S matrix is really hard. So as I mentioned before, the amplitude of the S matrix, so getting the amplitude of all these elements is actually not that bad. The blue ones are the ones that we actually display in the paper, just in case you're wondering. The color coding is how difficult it is in terms of how long the circuit is that will measure the phase of the S matrix. Of course, if the amplitude of the S matrix is 0, then you don't have to measure the phase. But if it comes out non-zero, then you have to measure the phase. It turns out for D4, the S matrix is always either positive or negative. There's no phases. But distinguishing a positive from a negative requires interference, and that's hard. So the depth can go from 23 way up there in the green zone down to the pink zone in the bottom, a depth of 171, which is kind of getting to be prohibitive. And how well can you actually do? And this is actually a kind of interesting result. In the green zone, where the depth is very short, of course you get the results almost exactly right, from the get-go, so it's not problematic. But as you go down to the pink zone, you start getting more and more error. But you'll notice that what you're doing here, so the expected target is -1, and you get the phase very close to right, but the amplitude is way suppressed. Why is that? Well, what's happening is you're losing amplitude to all sorts of other processes which you never see again. It's just lost into, to oblivion. And the amplitude just drops. You never recover it, but the phase of what you do get comes out right. So even though the depth of the circuit is really long, a depth of almost 200, you can still get the phase within a reasonable, not huge error.
That's still kind of
Why
a
does it
miracle,
work?
right?
What?
That's still kind of a miracle, though, right? That like all this noise you're losing this stuff too is still preserving.
It's still preserving that, yeah. And we look pretty carefully as to whether the noise model that they have is really has all the possible noises put in. I mean, it's quantum dot model. It should scramble that, And it's possible that the kind of noise they have is more complicated in just such a way to screw up the phase, and we just don't see it. But as far as when we presented it to them, they said, "Oh, it's because the noise model is too simple. You don't have this." And actually, we do have that. Well, you don't have this. Well, we have that too. But it is a simplified noise model. So there are some things that aren't represented, and it's possible that when you really do it, it won't come out this way.